Through the rainforest of Central America stretches one of the biggest man-made marvels on the planet. It's the mother of all shortcuts, the Panama Canal. 200 million tons of cargo pass through its gates every year. It's a masterpiece of canal construction. The Panama Canal owes its success to 4 key inventions found in a series of landmark canals. At the heart of each lies a major technological breakthrough that allowed ever bigger ships to navigate landlocked areas. One by one, traveling up the scale, we'll reveal the incredible stories behind these structures and the inventions that allowed each one to carry tons more cargo than the last. 4 ingenious leaps forward, from big to bigger, into the America's biggest. The Panama Canal is one of the world's key waterways. Over 1,000 heavily laden ships sail through it every month. Stretching through the heart of the Americas, this canal has changed the face of global trade. Ships traveling between the Atlantic and Pacific used to sail thousands of kilometers around Cape Horn. So in 1879, engineers planned to cut a channel through the Isthmus of Panama. This will shorten the trip from ocean to ocean to a mere 80 kilometers. Building the canal proves a huge challenge. The first attempt in the 1880s is thwarted by disease and disasters that kill thousands of workers. It takes more than 30 years before engineers finally manage to connect the 2 oceans. But when it's complete, the Panama Canal is hailed as the engineering achievement of the century. Now ships can sail from the Atlantic to the Pacific in just 8 hours, 40 times faster than the journey around Cape Horn.
Since the Panama Canal was open, over 1 million ships already came through this waterway. This canal generates $2 billion a year for Panama.
Today, 100 years after it was built, the Panama Canal is operating at its absolute limit. So now Panama is spending $5 billion to make it even bigger. This is the largest construction project in Central America. Engineers have developed an arsenal of new machines and technology to avoid the tragedies that plagued the construction of the original canal. The expansion project will double the canal's capacity to over 400 million tons per year. To understand how the Panama Canal can carry such a huge amount of cargo, we need to travel back in time to 17th century France. Here, engineers building the Briare Canal face a seemingly insurmountable problem: how to make water flow up a hill. At the start of the 17th century, Paris is recovering from the turmoil of civil war. As its citizens rediscover the finer things in life, the demand for wine and other produce skyrockets. But getting goods from the countryside to Paris on bumpy rural roads is slow and inefficient. So the French king decides to ship more goods into the city on the River Seine. He wants to connect the vineyards in the Loire Valley to the River Seine, which leads right into the capital. To link the two rivers, he plans to build the Briare Canal. But there's a problem. A 40-meter-tall hill is blocking its path. The obstacle leaves the king's engineer with some tough choices, as civil engineer Ed McCann explains.
If he goes round the hill, he adds 200 kilometres to the journey. And if he goes through it, he has to dig up the whole hill. So he can't go round it and he can't go through it. He's got to go over the top.
The king's engineer is determined to overcome this obstacle. On top of the ridge, he finds a lake fed by a spring. This gives him a constant supply of water he can channel down the hillside into the rivers. To stop the water from draining the lake, he contains it in a series of chambers. Now that he's controlled the water, he has to find a way of getting the wine-laden barges up the steps from one chamber to the next. Engineer Jem Stansfield demonstrates a simple solution to the problem.
They could have used a single gate like this, which is what they'd used on rivers to get over natural obstacles like rapids. It's called a flash lock, and pretty soon you'll see why. The idea is when the gate is removed, the head of water at the top weirs over the step, and the big cushion of water it produces is enough for the boat to be able to ride up it and over it and onto the higher level. But it all happens very quickly. There we go, it's coming through. The boat has to come through that raging torrent, over and into the reservoir above. But it's not easy. The boat has to literally be hauled through the water, and it's very dangerous. If it looks bad going up, going down, it's like being flushed down a toilet. And even if the boat survives, any delicate cargo like wine could get smashed to pieces. Which is a reason why these gates could never be more than a metre high, because above that level, the torrent would simply be too big, too dangerous, and the results could be catastrophic.
By simply adding a second gate, engineers create a chamber in which they can slowly raise the water level and lift the boat up. This invention, called the pound lock, exploits the power of the water to get even the heaviest boats over a step in a canal.
So now the boat's in the lock, but we're down low, so we've got to fill the lock up with water, and the first thing we've got to do is shut the back gates. Once the gates are shut, what I have to do now is fill the lock up with water, and I do that by turning this handle, which opens a sluice gate and lets the water in. So I do that. I can see the water start coming out below now, and it's pouring into the lock now.
As the water floods the chamber of the pound lock, it pushes the boat up to the next level of the canal.
When the water levels are equalised, it's really, really easy to open. Even my kids could open it.
The pound lock conquers the hill blocking the Briare Canal. Engineers build 12 of these locks to lift the barges from the Loire Valley up to the top of the incline. And to get them down a steep drop on the other side, the engineers build a structure never seen before. They join 7 pound locks into a giant staircase that gently lowers the precious cargo down to the bottom. With their biggest obstacle behind them, the barges now have a clear run to Paris.
This is it. Within a short time, it was being used by 4,000 barges a year. In fact, it was so successful, they had to build a newer and even bigger canal to carry bigger boats. This fantastic idea was responsible for the Parisians getting all the wine they could drink. Cheers.
On the other side of the world, the Panama Canal uses the Briare Canal staircase lock concept, but on a massive scale. Each ship passes through 3-pound locks that raise it 26 meters from the ocean to the top of the canal. Once the ships have cruised across Panama, another set of locks lowers them into the ocean on the opposite side. The lock chambers are so big, they take construction to the extreme.
When engineers built this set of locks, they were the largest concrete structures in the world.
The lock gates are as tall as an 8-story building. Their mighty steel plates are held together by over 3 million rivets, as many as the Titanic. It takes over 4 years to complete the gigantic locks. When the canal opens in 1914, the largest ships of the time can easily fit inside its huge chambers. Today, there's a breed of ship that takes even these monster locks to the limit. They're the biggest ships that can pass through the Panama Canal, and they're called the Panamax. Squeezing these monsters through the canal is a tricky task, which calls for an elite crew of sailors. Joshua Aparicio is one of the few highly trained pilots who can steer ships through the locks safely.
Here is the moon ray. That's my job for today. Roughly, I will have 2 feet each side to work a space. We're talking about this much between the wall and the hull of the ship.
The captain of the tanker hands the wheel to Joshua. As he maneuvers the ship into position, the lock crew hook up the ship to 6 powerful locomotives standing by on the dockside.
The locomotives guide the ship. They keep the ship in the center of the locks. The pilot will be telling the operator on the locomotive what to do, when to slack the cable, when to brake. They're very powerful. They use 2 motors of 290 horsepower. It's a lot of concentration because you don't have that much space. This is the rail where they get their power, 480 volts, yeah.
Once the huge gates are shut, over 1 million bathtubs worth of water floods into the lock chamber, lifting the ship. It takes 2 hours for the Moonray to climb all 3 steps to the upper level of the canal. With a convoy of ships queuing to enter, any delay could cause total havoc. Carlos Patterson is the man in charge of keeping the locks working 24/7.
It's extremely important for us to maintain the locks running at all times because we have a lot of customers going through. We have backlogs of ships. So for us, it's very critical. We have 5 minutes of a benchmark to do any kind of repair that needs to be done.
One of the valves that let water into the lock chamber is broken. Carlos's team of divers must fix it before the next ship arrives.
It's very critical. We need to have this happen very fast. And we have a ship coming from Pedro Miguel.
Underwater, the diver works in almost zero visibility.
Sometimes simple tasks that we could do in minutes, down in the water, in the dark. It's a little bit more complicated.
The team finished this repair in the nick of time, but the expansion project is about to double their workload. The current locks form a bottleneck, restricting the size and number of ships that can pass into the canal. So engineers are building another set of locks with even more shipping lanes. At the Pacific entrance to the canal, teams of workers are digging out a 2-kilometer-long pit, the bed for a true megalock. The chambers will be twice as big as the old ones, and designing steel gates for them is a tough challenge. Traditional swinging gates would have to be so long and heavy that they could break off even the strongest hinges. So the engineers planned to install sliding gates. But if these gates were made of solid steel, they might crush their supports. Jem Stansfield demonstrates how the canal builders use fresh air to solve the problem.
I've got here 2 concrete blocks. Now, they're the same size, the same shape, and made from the same material. But when I put them in water, there's a significant difference. Sinks like a brick, just as you'd expect. But this one, it floats. But what is it that makes a block of concrete float? Let's chop it open and have a look. There we go. It's completely hollow. And the thing is, hollow shell structures like this, they retain most of the strength of the solid version, but at a fraction of the weight.
A hollow chamber inside the steel gate, filled with air, cuts the effective weight by half. Now a small trolley is all it takes to prop up the gate and let it glide in and out effortlessly. When the new locks are complete, ships carrying twice as much cargo as today will be able to pass through here, upgrading the Panama Canal for another century of operation. Back in 1642, the Briare Canal proves to the world that canals can climb over hills. But this feat requires plenty of water to fill up the locks. To build the Bridgewater Canal in an area short of water, English engineers must learn how to save every last drop. In the 18th century, northern England is the heart of the industrial world. Demand for coal to power steam-driven machines far outstrips supply, because coal is still being moved in the old-fashioned way, on horseback. Coal miners could make a fortune if they can solve this problem.
Moving coal by horse is a tricky business. I mean, a horse can't carry much coal, 3 or 4 bags and it's done. And these mines wanted to move so much coal, horses weren't going to cut it. What they needed was something else, something like a canal. Once you've got your canal, you can have literally convoys of barges coming out from the mine, every barge carrying 30 tons of coal, but pulled by just 1 horse.
Engineer James Brindley gets the job to build a canal from a coal mine in the countryside to the industrial centres of Manchester and Liverpool. But there's a problem. There are no rivers near the mine. Brindley must pump groundwater out of the mine shafts to feed his canal. He surveys a perfectly flat route from the mine to Liverpool and Manchester. but discovers that some of the soil is so porous he risks losing his precious water back into the ground. Jem Stansfield demonstrates the problem.
What you've got to remember is a canal is not a river. It doesn't really flow. It's essentially a long, stagnant pond. Now, that gives the water plenty of time to seep away. And I've got 2 bowls here with soil in. Now, if I pour water into this one, you'll see, it slows the water down but doesn't stop it just draining away. And that's because of the way that soil's made up. It has relatively large particle size with gaps between it, and there's no difficulty for the water to find a way through. Now, what Brindley needed to do was figure a way of stopping that from happening, and that relied on one thing: clay. Now, the thing with clay is the particle size is particularly small, and they're packed together extremely well. And that packing means the water struggles to get through. It's practically impermeable. So with a layer of clay in here, those fine, densely packed particles make it pretty much impermeable.
Brindley lines the porous areas of his canal with clay to make it watertight. But along the route, he hits another obstacle: the River Irwell. If Brindley builds locks down to the river, they will drain away water every time a barge passes. And there's no water source to fill up the canal on the other side. So he builds a stone aqueduct to keep his canal flowing across the river. Brindley's obsession with saving water makes the Bridgewater Canal a huge success. But 100 years later, as ships get bigger in the river below, Brindley's stone aqueduct needs an upgrade. To allow tall ships to pass, engineers could simply raise the structure. But that means building locks, which will waste precious water. So instead, they demolish the aqueduct and build an island into the middle of the river. On here, they install an iron pillar connected to an iron trough that carries the canal across the river. The new aqueduct is no taller than Brindley's old one, but it has a clever trick up its sleeve. It can swing open, so even the tallest ships can pass.
And this is it. The world's first swing aqueduct, still working perfectly 100 years on.
The aqueduct pivots on a single pillar that carries the full weight of the bridge.
This is a fantastic piece of Victorian engineering. It's made out of wrought iron, riveted together. We've got a steel rack here and cast iron roller bearings, and you can see them all. The whole thing weighs about 1,600 tons. That's about 4 fully laden jumbo jets. But what really amazes me is that this huge contraption can swing out of the way of oncoming ships in less than 5 minutes.
Before the aqueduct can swing open, the keeper must close heavy iron gates to seal the canal tightly at either bank. Additional gates on the aqueduct then trap 800,000 litres of water inside the trough. Two steam-powered hydraulic engines control the speed of the aqueduct, swinging it smoothly to ensure no water spills out.
The Bridgewater Canal was a huge success, and it carried over 3 million tonnes of cargo. This amazing machine kept the Bridgewater Canal on the level and avoided the need for water-hungry locks.
In the 19th century, the engineers building the Panama Canal face an obstacle course even more challenging than Brindley did. There is no flat route across central Panama. A range of mountains and the raging Chagres River block their path. Rather than building lots of locks over this terrain, they opt for a radical solution.
What the engineers decided to do is to use the Chagres River, take advantage of the rain that we had in Panama to build the Panama Canal.
The key to taking the canal across central Panama is the mountain range around the Chagres River, which forms an almost perfect basin. Into the gap where the river exits this basin, the builders piled two gigantic walls of rocks. They fill the gap between them with clay, which hardens into a waterproof wall. This forms the core of the biggest earth dam of the time. Behind it, the fast-flowing Chagres River floods to form the gigantic Gatun Lake. Now ships can simply sail over the Panamanian jungle and not a lock in sight. And here it is, Gatun Lake. It holds over 60 billion bathtubs worth of water, just enough to feed the thirsty locks.
Every time a ship transits through the Panama Canal, 200 million liters of fresh water goes into the oceans. 100 million liters into the Atlantic side, 100 million liters into the Pacific side.
The expansion project will add 6 more locks, and Gatun Lake does not have enough water to feed them all. Rather than double the size of the lake and flood precious rainforest, engineers must make the new locks more economical. Engineer Jem Stansfield shows how locks can recycle water by feeding it into special holding tanks.
The problem with locks is the water to fill them always has to come from the upper level of the canal and then gets lost to the lower level as the water drains through for the boat to continue. But who says all the water from a lock has to be lost into the canal at the bottom? Have a look at this model. Now, this is my lock here. If you imagine the boat's coming in at the top and it wants to leave at the bottom, so it goes into the lock, the water then gets drained out of the lock so the boat can lower right down here and then carry on its journey. If I open this tap here, the water in the lock now starts draining into this holding tank. Now once the boat gets to this level here, I can then open that one, drain water into this holding tank, and then when it gets down here, open that one and drain water into this holding tank. There we go. The boat's down here now, and I've stored a good proportion of my water. So I can start filling the next tank. Another 20% of the water saved there. The boat's more than halfway down the lock now, and this last chunk here is the only water of the lock that actually gets lost. And here's the really clever bit. When I want to refill the lock to raise a boat to the top so it can continue in the upper canal, I can take the water out of my holding tank. So first, I empty the lower one. Once I've got this chunk of water from here into the bottom of the lock, I can then shut this tap off and open this one. And then this chunk of water goes into the next level of the lock, and this one here, and the lock is 60% full just from the water that I've saved from the boat on the way down.
This is the pit where the holding tanks of the new Panama Canal locks are taking shape. They're gigantic, covering an area of 43 football fields, and will take 4 years to complete. But they'll make sure that the Panama Canal never runs out of water, even with twice as much cargo passing through it. Back in 1761, the Bridgewater Canal shows that saving water is the key to a canal's success. But as world trade expands, cargo ships grow larger, and canals must keep up with them. To build a canal that can carry some of the biggest ships in the world, engineers in Manchester, England, have to reinvent the art of digging. In the late 19th century, the city of Manchester faces a big logistical problem. Its main rival, Liverpool, charges extortionate docking fees for ships with cargo bound for Manchester. So entrepreneurs plan to build a canal on which big ocean-going ships can sail straight into the heart of the city. The Manchester Ship Canal will be the biggest waterway ever built and require a colossal amount of excavation. Chief Engineer Edward Leader Williams recruits the best diggers in the country, the navvies. These men are capable of almost superhuman feats of endurance and can shift hundreds of buckets of earth a day.
A whole army of navvies descended upon Manchester, looking for work building the canal. But your average navvy will shift about 8 tons of soil a day, and they would have to move over 80 million tons of soil to build this canal. Simply put, there just weren't enough navvies to do it in the time they had.
Chief Engineer Williams invests in a brand new machine designed to make digging easier. It has a huge steam-powered excavator belt that gouges out the earth to carve a deep bed for the canal. Then it drops the soil onto railway trucks that carry it away. One of these steam monsters can dig out more soil than 50 navvies together. And with a battalion of steam excavators in place, the Manchester Ship Canal takes shape rapidly.
This would have been a hive of activity with hundreds of machines and thousands of men all beavering away. And it was going pretty well until the great flood of 1890, which washed away the banks and brought thousands of tons of silt into the channel. And all of these wonderful machines that had been brought over to do the work were completely trashed.
Heavy rain causes nearby rivers to break their banks, permanently flooding Williams' construction site. He needs to find a way to carry on digging underwater. So he commissions engineers to make his excavators float. They suspend the excavator belt between 2 barges and anchor the conveyor belt to 2 ships that follow behind. Now the buckets can reach the bottom of the flooded canal to remove the soil and carry it away to the banks. This is exactly what Williams needs to finish his canal.
These floating excavators are basically dredgers, and they're a huge success. They actually speed up construction because they're easier to move around than the land-based excavators.
When the Manchester Ship Canal is complete in 1894, huge ships can sail directly into the centre of Manchester. The city, 50 kilometres from the coast, becomes the 3rd busiest port in the UK and gives it the edge over arch-rival Liverpool. When work on the Panama Canal begins in 1880, 80,000 workers are recruited from all over the world. The 80-kilometre-long channel is twice as big as the Manchester Ship Canal, and digging it proves a hellish task.
Over 30,000 workers died to build the Panama Canal. The majority of them died of tropical diseases like malaria and yellow fever.
Many of the men are killed in an area near the Pacific Ocean, where tall mountains block the canal's path.
We're in the heart of the Continental Divide, the center of Panama. The land rises over 80 meters above the level of the water.
Workers use powerful machines to dig through the rock. An army of mechanized excavators drive a deep chasm through the mountains, known as the Culebra Cut. They remove over 100 million tons of earth and rock. Huge dredgers carve out a channel 4 stories deep below the water. Today, engineers working on the expansion project have to make the canal deeper still. They've hired a mean machine to attack the tough rock under the Panama Canal. Cutter suction dredger D'Artagnan. The dredger has a cutter head that reaches 15 meters down to the canal floor. Here, its sharp cutter teeth slice through the rock and break it into small fragments.
This is the D'Artagnan's secret weapon. This is a cutter head designed for rock. It's a 7-blade. It's for heavy duty stuff. It's something we've never done before, so hard.
Even though the cutter teeth are made of toughened steel, they don't last long on this job.
You see, it's a one cutter teeth. This is a new one, so you clearly can compare what we already lost from the contact with the rock, and you see all the trace of the rock. You see the steel is a light blue due to the friction of the teeth on the material.
The crew must constantly replace all 70 steel teeth, sometimes every half hour.
It's like to be a dentist.
Each tooth costs up to $250, making this expensive canal surgery. As the dredger gouges out the rock from the bottom of the canal, a powerful pump sucks the debris up to the surface. Here, it shoots into a pipeline which takes it away from the dredger and spits it out onto the shore up to 10 kilometers away.
So in the back you see 600 meters of floating pipeline. This is our way to send the material away from the dredging area.
At the end of the pipeline, this mega dredger shows how tough it really is.
This is what is currently being dredged. It's basalt. It is the hardest rock we can find in the area. Rocks like this that are currently coming out of the pipe which we see behind me. The material coming out is around 1,000 to 2,000 cubic meters of soil per hour. So by the time that we are finished here, the D'Artagnan will have dredged another 5 million cubic meters of rock like this.
Back in 1894, the Manchester Ship Canal proves that you can dig massive canals even underwater. Today, as canals carry more and more cargo, there's enormous financial pressure, especially on the biggest canals in the world. Ships can pay hundreds of thousands of dollars to use the Panama Canal, so the operators must make sure it's smooth sailing. In April 2011, disaster strikes at the Kiel Canal in Germany. 2 large ships collide and block the canal. It takes 5 hours to clear the blockage before Europe's biggest canal can reopen. The delay to shipping costs thousands of dollars in lost revenue. At the Panama Canal, a similar delay would cost millions. To prevent expensive snarl-ups, they use a network of technology, coordinated from the nerve center of the canal. This is marine traffic control. Teams of highly skilled operators work round the clock to make sure ships get through without a hitch. Each ship navigating the Panama Canal is fitted with a GPS beacon so the operators can track its progress, even in zero visibility.
All these little dots are ships. I can pick the ship that I want and actually zoom in and see what he's doing. I can see what the speed is over ground. And if I want to check and see at what time he's going to get it to a certain place, it'll give me an estimate of where he's going to be there.
The team must keep a close eye on the canal's bottlenecks.
Critical places in the canal is Culebra Cut and the locks. We always try and keep Culebra Cut and the locks as protected as possible. If anything goes wrong in Culebra and shuts down the canal, we got problems.
If a ship encounters problems, a fleet of 24 tugboats is on standby to rescue them. Raymond Robinson is in charge of the tugs, and he's just received a call that a broken-down cargo ship is blocking the canal's Pacific entrance.
Vamos.
Tugboat 6 Aola races to intercept the stricken ship.
Get aboard and do the ship has engine failures, so now the 6 Aola is alongside, assisting him, but he's not going to the locks.
The tug operator can't allow the defective ship to drift into the shipping lane, so he uses the raw power of the tug to bring it to a halt. Once the huge ship is under control, the tug turns it around and pushes it back into the open sea. For Raymond and his tugs, life is about to get even busier. The expansion project will double the capacity of the canal and allow much larger ships to enter. But one area, the Culebra Cut, will always be a hotspot. An accident in this narrow channel could cause total gridlock.
We keep it dead slow ahead and steady as she goes, man.
To prepare the pilots to navigate the largest ships through the canal without a hitch, they train up in a multi-million-dollar ship simulator.
Okay, approaching the bridge.
Today, pilot Ricardo Trand gets to try one of the new ships out for size. It's twice as big as the one he usually pilots, and it's just had a simulated engine failure in the Culebra Cut.
Mr. Pilot,
yes, sir.
we lose engine, sir.
Okay, break, south 12, south 12. We just lost the main engine. We'll do our best, huh?
Apparently we also lost the engine. Let it go.
Starboard anchor.
Anchor down, Captain.
Okay, Captain, we need you to sound 5 short blasts emergency signal.
Without power, the ship is doomed. The best the pilot can do is to beach the monster on the banks of the cut
Bow reach.
and call in the cavalry.
Break. We need extra tug assistance if you can.
Hopefully, the training in the simulator will stop accidents like this from happening in the real canal. The expansion project will give a new lease of life to the Panama Canal. But before it's finished, the workers here must move millions more tons of earth and pour millions more cubic meters of concrete. When it comes online, this will be by far the biggest canal in the Western world, until someone builds an even bigger one.